Hello, good afternoon. Am I audible?
Yes, sir.
Good afternoon and welcome to our lecture on advanced power electronics. Last time we discussed the applications of single phase voltage source PWM rectifier and a three phase voltage source PWM rectifier, and one of the application we have discussed the single phase applications as well as one of the three phase application we discuss is a induction motor drive or the AC drive. It may be induction, synchronous, or the brushless. And we have used here a PWM rectifier and the PWM inverter. And this is our PWM rectifier, a PWM inverter. And our interest is our source current should be sinusoidal and power factor should be unity, and that is obtained with the help of this PWM rectifier. Whereas we are having a inverter at the machine side, and this will control the voltage and frequency to control the speed of the motor. We achieve the four quadrant operation, so we can run the drive in both directions, forward as well as reverse, and we break the drive when it is running in forward direction as well as reverse direction. And this braking is a regenerative braking. During braking, a power generated in the machine that is given to a inverter that will work as a rectifier, and this rectifier will work as an inverter, and power will be fed back to the supply. Here source currents are sinusoidal. Similarly, here our machine currents are also sinusoidal. And we have seen how to get the braking whenever we are reducing the speed, particularly when we quickly reduce the frequency, synchronous speed will change, rotor speed will remain same, then slip will become negative, and machine will go into a generator mode. And now this is the drives are available. One of the circuit diagram we have shown is the drives from ABB, and here we are using the PWM rectifier, front end PWM rectifier, and the PWM inverter, the DC link capacitor, and here we are having the switching harmonics, and for that we are using the filter, and that name of the filter is LCL filter. Okay, so that we can reduce the uh, switching harmonics, and our input currents are a sinusoid and they are in phase with supply voltage. We obtain unity power factor, and motor can be speed can be controlled below base speed as well as above base speed. We can have a four quadrant operation with a regenerative braking. So this is one application where we use a voltage source, a PWM rectifier. Now let us go for another example where we can go for application of a three-phase voltage source, a PWM rectifier. And here one application is variable speed, constant frequency power generation. So we generate the power with the help of wind turbine, and this power can be fed to the grid. So almost all our 90% wind farms are grid connected. Almost 95% wind farms we are having, they are grid connected, so they will feed power to the grid. We are having two types of uh, horizontal axis machines. One is a constant speed and other is the variable speed. So and now trend is we have to use the variable speed uh, wind turbine machine. In that case, the speed of the turbine will change as per the wind velocity. So limits of wind velocity, you are knowing limits of wind velocity is from 4 meter per second or 3 meter per second to 15 meter per second. Normal range is cutting speed, you can call it 3 meter per second, and rated speed is a 15 meter per second. And from 15, our power generation is also possible by a 25 meter per second. So normal particular wind speed, we are having 3 meter per second to 25 meter per second. And we are going for a variable speed option so that we can capture the maximum energy from the wind. Here we have seen that as wind speed changes, let us go for next slide here. So this graph indicates we are having a power output of the wind turbine versus the speed of the turbine for different values of wind speed. So the graphs, if you see it, these graphs, particularly for a first graph we have shown is 6 meter per second when wind speed. Then next we are having 8 meter per second. Then this graph we are having a 10 meter per second, and then we are having a 12 meter per second. So our wind speed may be changing, and correspondingly we have to extract the maximum power, possible maximum power from the wind. So if you see it here, when wind speed is 6 meter per second, we have to operate here. When particularly 8 is there, we operate at point A. When 10 is there, we operate at point C. And similarly for here for 12 meter per second. Means our wind turbine speed has to change so that we can capture the maximum power from this. Now here if you see this diagram, we are using the induction machine. A cage induction machine we are used here. There are so many options for wind turbine machines, but here present case we are discussing the induction machine, and we have to give the supply to the induction machine, particularly for its excitation. It takes a reactive power from the grid for its excitation. So now we are having a stator winding, and these are connected to the PWM rectifier. We are having a DC link capacitor, and then we are having a PWM inverter, which will through a transformer, it will be connected to the grid. Now here, always whenever we are having natural resources, either solar or MPPT, we have to operate at maximum power point so that we can extract the maximum power from this resource and we can generate the power. And for here, our turbine speed is vary. How we extract the power, maximum power, by adjusting the slip of induction machine. Here we are adjusting the slip of induction machine. Basically, it is a varying at the variable speed, and to that variable speed we adjust the slip such a way that we can extract the maximum power from this. So how we here we have seen that we are using a PWM technique here, particularly for this, and we can decide frequency or a frequency of voltages at ABC, what we can call it here. We can find out frequency, and it is possible with the PWM technique. It is possible to adjust the frequency of this PWM rectifier. It is a rectifier, but we can have a AC here. Voltage appearing here will be AC. Its frequency can be adjusted. As this frequency is adjusted, we have seen that based on that frequency we are having the synchronous speed. Who will determine the synchronous speed of induction machine? Particularly this PWM rectifier, which is having a control here at the input side. We can control the frequency of that by switching of this speed IGBT. We control the frequency. As we control the frequency, our synchronous speed will can vary, and our rotor speed will be, rotor is connected to a wind turbine. So by knowing the wind turbine speed or rotor speed, we adjust the frequency of this PWM rectifier such a way that our slip will be such a that we can get the possible maximum power from the induction machine. So here if you see here, so we have seen that this graph particularly indicates we have to operate the turbine at variable speed to as per the wind speed varies. As our wind speed varies, a turbine speed has to increase to extract the maximum power. Now available maximum power we can extract from the induction machine. If you look at this will be an induction generator characteristics, output power versus slip. So if you see it here, x-axis we have given the speed. If you see here, x-axis we are having a speed, and this speed is given in per unit or in terms of rated 100% speed. Here 100% speed means a synchronous speed. 100% speed means a synchronous speed. And at synchronous speed, this green waveform graph indicates the how is the power output, and it is also given in terms of per unit power. This is a watts, we can call it a power, active power. It will be given in watts, and this is a green waveform which will indicate we are operating at a speed higher than synchronous speed, so sleep is negative. And here a particular characteristics we have shown it here, where our sleep is just 2% for a 100% output. And we have seen that this particularly red waveform, that will be the reactive power requirement with the sleep. Or we require minimum reactive power when the sleep is zero or at synchronous speed. As we sleep increases, definitely the reactive power requirement will be also increased. So here our objective is, with the help of this PWM rectifier, we adjust the sleep of the induction machine. We adjust the sleep, or we adjust the speed. Speed is given by a particular turbine speed, but we can adjust the ns by adjusting the frequency. So synchronous speed is adjusted, and rotor is allowed to rotate at its maximum speed, and we adjust the frequency of stator, and so that we can extract the power generated from the wind. And now we have seen that how to extract the power, maximum power. And for extracting the maximum power, we have to adjust the sleep of Ig. How we adjust sleep of Ig? Excitation of Ig is provided by PWM rectifier. So we have seen that this particularly excitation to this machine is provided by this PWM rectifier. And depending upon rotor speed is depends upon the wind speed. That is not in our hand, and we adjust the Ig excitation frequency provided by PWM rectifier is adjusted, so that we can adjust the sleep, and we can extract the maximum power from this. So stator flux speed is controlled by the PWM rectifier. It means that we control the sleep of Ig, and we extract maximum power from this. Once we extract the maximum power from this, we have to control the line side inverters, or you can call as a line side PWM converters. And here we have to adjust. Here this is a control in such a way that the capacitor voltage is maintained constant. We are working on this, why we have to maintain the capacitor. So here if you see here at capacitor, a power is coming from wind turbine. Here power is coming from wind turbine. I'll just try to sketch out. So power is coming from wind turbine is given by this, whereas power going to the grid is given by this. If these two powers are different, let us assume that power coming from the wind turbine, or power coming from induction generator, and power going to the grid. If there is a mismatch, if this power is high, if this power is on the higher side, if this power is higher, it means that this power is more. Power coming from the induction generator is more. In that case, power going to the grid is, let us say, slightly less. Then difference of power will be accumulated across the capacitor, and capacitor voltage will increase. Okay. So whenever power coming from wind turbine is higher as compared to power going to this, then capacitor voltage will increase. Now let us assume now power coming from this is a less, power coming is less and going to this is higher, then there will be deficit of power, and here the capacitor voltage will decrease. So voltage across the capacitor depends upon the how much power coming to the capacitor and how much power going from the capacitor. And our objective is to maintain the constant voltage across the capacitor. What is meaning of constant voltage across capacitor? So whatever power comes from turbine generator, it gives to the grid, and that is achieved with the help of maintaining the voltage constant. So why we have to maintain the voltage constant? Is it clear? Why we can maintain the voltage constant? Why we can maintain the voltage constant? Anybody? Am I audible? Hello.
Yes, sir.
So why we have to maintain the capacitor voltage constant? If when capacitor voltage will be maintained constant, power coming to the capacitor, power coming to the capacitor from wind turbine and power going to the grid, they are equal, then a voltage across the capacitor will be a constant. If incoming power is higher, outgoing power is less, capacitor voltage will increase. Or if outgoing power is more but incoming power is less, capacitor voltage will decrease. So here we maintain the capacitor voltage constant so that whatever extracted power is feedback to the grid. Extracted power is feedback to the grid. What is the nature of currents in the stator winding of induction machine? What is the wave of currents in the stator of the induction machine? Is it a sinusoidal or non-sinusoidal? What is the nature
Sinusoidal.
of
Sinusoidal, sir.
a current in the sinusoidal? Whereas also in the grid, to the grid, we can give the sinusoidal current. One another benefit of this particularly inverter when connected to grid, we can supply active power, but at the same time, it is possible to supply reactive power also. So here this our PWM inverter will give both powers. As per the requirement, we can have a P coming from wind turbine, we can give it. But as per the grid requirement, we can give a Q that will be plus Q as well as minus Q is possible. So both Q can be possible with the help of control. It is possible that we can reactive power we can give to the grid or we can extract the reactive power, absorb the reactive power. So that both things are possible. That is the benefit of this particular PWM inverter whenever connected to the grid. So it will give the active power whatever came from a wind turbine, but as per the grid requirement, sometimes grid is required, suppose a reactive power support is required, then this inverter also provide the reactive power support. Or sometimes grid voltage is increasing, we have to absorb the reactive power, then also it will provide the negative q. So positive q and negative q will be also possible to give, this will give to the grid. So that is the advantage of this particular scheme. So this is we explain why we have to capacitor voltage we have to maintain it constant. So power received from the wind generator and power given to the grid, that should be the same. Under that condition, our capacitor voltage will be maintained constant, and that's why our control strategy will be to maintain the capacitor, to control the inverter. To control this inverter, our control objective is to maintain the DC link voltage constant. So whatever extracted active power will be feedback to the grid. So any question? This will be on the three-phase PWM voltage source rectifier. Any doubt? We have discussed two applications. One is the AC drive and other is the variable speed, a constant frequency wind power generation. Any doubt? Now let us go for just we revise some of we require current source, DC current source, and the application of DC current source is the current source inverter CSI. Have you studied CSI in the power electronics, or you have studied this drive? Is it this drive you have studied in case of industrial drives and control?
Yes, sir.
So this is a line commutated current source inverter or LCI fed synchronous motor drive. This particular we are drive is having a speed control of synchronous motor. And here particularly we are using this LCI fed synchronous motor drive. I will write it as line commutated inverter. LCI line commutated inverter fed per synchronous motor drive. Sorry, not load commutated inverter fed synchronous motor drive. And here we have seen that. So this is a line converter. If you see here, this is a line converter. It will be a 6 pulse converter. Is it right? So this is our a 6 pulse converter, and this is also a 6 pulse converter. Both we are having a 6 pulse converter. Both will be having a 6 pulse converter, and they are connected through a large value of inductance, filter inductance. So this whole scheme is of a particular with the help of thyristors. This whole scheme we made with the help of a thyristors. And this will be, now let us assume that we have to discuss about the motor operation. So our power is flowing particularly power is flowing from supply side to the motor side. Let us assume that this is our power flow. This is the direction in which power is flowing from supply to the motor. Now this 6 pulse converter will work as a rectifier. I will write as R. This will work as a rectifier, whereas this will work as a inverter. This will work as a inverter. So we are doing the 6 pulse full control converter working as a rectifier, and this will be a 6 pulse converter now working in inverter mode. Okay, working in inverter mode. So this is working as the inverter mode, and when you want to inverter mode, its alpha should be how much? It should be above 90 degrees. Alpha should be a greater than 90 degrees. And here we have seen that we are using a thyristorized and the inverter, and we have seen that we are using the load commutation. So we are having the 3 methods of commutation. What are 3 methods of commutation to the thyristor? 3 methods of commutation to the thyristor. Can you recall what are the 3 methods of commutation? Turning off the thyristor. What are 3 methods of turning off thyristor?
Current commutation, voltage commutation, and load commutation, and
How we can,
complementary.
okay, one we can call as a line commutation. This particularly water converters, they are coming under line commutation. Supply voltage, you see supply. Our converters, all 6 pulse, 3 pulse, 2 pulse, full control converters, they are our rectifiers, they are line commutation is used. Means supply voltage itself is used to turn off this. So that is line commutation. Whereas one is we are having a force commutation. We are having some methods. We use the LC components to turn off the thyristors, and that we can call as a force commutation. And now here we are using the load commutation. So load voltages. Which are the load voltages here? So synchronous motor voltages. Synchronous motor voltages. Let us assume that this will be ABC terminals. The synchronous motor terminals itself will be used. The voltage available at the terminals is used to turn off the particular this line commutated inverter. Load commutated inverter. For that, what is our requirement? Requirement is that synchronous motor should work on leading PF. So here our PF should be leading. So a leading power factor. Synchronous motor should work at the leading power factor. So how to adjust the power factor of synchronous motor? How we adjust the leading power factor of the synchronous motor? How we adjust the leading power factors?
Changing field excitation.
Okay, so we over excite it. We increase the field current. So under excited synchronous motor will work for lagging power factor, and over excited synchronous motor work with the leading power. So here, when you want to implement this particular control scheme or speed control scheme, our power factor of synchronous motor should be a leading one. And when the terminal voltage, when power factor is leading, this terminal voltages can be used to turn off this inverter, and that particular commutation we can call as a load commutation. This we can call as a load commutated inverter, load commutation. So both are thyristors, but a commutation will be a load commutation, and for that synchronous motor should operate at the leading power factor. Now this will be operation here, and now we have seen that this particular motor, it can work in 4 quadrant, means our power flow can be a reversed. We can reverse the power flow. This is the power flow is reversed during the regenerative braking. Our power can flow from machine to the grid. Here we have known that our thyristors are unidirectional. So this ID is not reversed. ID is not reversed. Let us assume that for particularly motor operation, this is the terminal voltage here, and correspondingly this will be terminal voltage particularly at the inverter side. Whenever we are going for a particularly a regenerative braking, then direction of current will remain same. But here, a terminal voltage now will reverse. This will become minus and this will become plus, particularly for this power. When your power is flowing this side, particularly our voltage will change. Voltage polarity will change. Current will remain same. Okay. And so it is possible straight way, it is possible 4 quadrant operation of drive synchronous machine, run in both directions and brake in both directions, and while braking this we can feed back energy back to the supply. What is the nature of source current here? Can anybody tell what is the nature of source current at the 3-phase AC input side? What will be a nature of source current?
Cauchy square wave.
Correct. So here our source current, that is our Cauchy square wave. So our current, particularly we are having a Cauchy square wave, 120 degrees positive current, 60 degrees zero, again 120 degrees negative current. This will be the wave shape of our source current, and this is a major concern. So what is the drawback of this drive from power supply point of view? It injects harmonics 6m plus minus 1, that we are knowing. Harmonic spectrum is 6m plus minus 1. And what is the THD of source current? Around 31%. Okay. And now our interest is this particular drive. This particular drive we replace with a PWM rectifier, current source PWM rectifier. Current source PWM rectifier. So both these, instead of using the thyristors, we can go for a current source PWM rectifiers. Current source PWM. What is the purpose of current source PWM rectifier? What is the purpose? Here when we use a current source PWM rectifier, our source currents are sinusoidal and power factor is unity. Here power factor, what is the formula for power factor of 6 pulse converter? Power factor, how we get it power factor? 3 by pi cos of alpha. Is it right? So this is a power factor of 6 pulse converter is given by 3 by pi cos of alpha. Okay. So here power factor and the harmonics, these two problems, and our interest is we can have a current source. We are having a current source rectifier such a way that it will take a sinusoidal current from the supply and it will give to a DC current to the load. So this is a scheme already last time we had discussed. So we just here is a closed loop control. We are not going to discuss it, and we have shown it here. LCI fed synchronous motor drive. Whatever this is the scheme you have studied, particularly in industrial drives and control. And what is the requirement here? Motor should operate at a leading power factor. Why motor should operate at leading power factor? We want to commutate the turn off the thyristor with the help of machine terminal voltage, and for that it should operate at the leading power factor. That's why this scheme we can apply only for field wound synchronous motor. It is not possible for BLDC. It is not possible for the induction motor. And we have seen that this is particularly high power rating. This drive particularly are used presently. They are used and they are having in megawatt range, medium voltage 6 kV, 1 megawatt, something like that. And it is possible that 4 quadrant operation we just see, and we are having a wide speed and power range. And what are the disadvantage? Not suitable for induction motor drive, because we cannot operate induction motor at leading power factor. may not be cost effective for small capacity, and we require a large space as compared to standard drive. But these particularly drives are in use. Where they are used? A continuous operating drives, where we require a continuous operation, and the applications are fans and pumps. What do we understand by fan and pump? Here, not our fan which we are using in our house. Okay, this will be a particularly fans used in thermal power plants, fans used for boilers, that we can call as id fan and the fd fan. So these fans are particularly we are using in case of thermal power plants. id induced draft, id fan, induced draft fan, and then we are having fd. fd is the post draft, post draft. So particularly post duct, particularly these fans, high capacity fans, we can use for air circulation in boilers. Their rating may be a few megawatts. Also high capacity pumps, high speed compressors, reciprocating compressors, wind tunnel farms, fans, rolling mill drives, and the extruders. These are applications, particularly high power applications, where we can use this LCI FET drives. And now we have shown it here, another for low power induction motor drive. uh, how we can use this, again a CSI induction motor drives, auto sequentially commutated CSI induction motor drives. And here this will be our current source, this our rectifier. This 6 pulse rectifier is working as a current source. By putting a large inductance and a closed loop control, it will work as a current source, and this current source is given to a current source inverter, and name of this inverter is auto sequentially commutated inverter. Okay, we are not going for this, and so this particular also we can use for speed control of induction motor. This is our induction motor. Again here, what is the drawback? Here drawback is our source current is quasi square wave. So our current is the quasi square wave, and our power factor is 3 by pi cos of alpha. So this is the drawback from the power supply point of view. So now source side drawbacks of our current source rectifier using thyristors, and these drawbacks we have listed here. 6 pulse converter we are using, and this 6 pulse converter takes a quasi square wave current from source, and this quasi square wave harmonic spectrum we are having 6m plus minus 1. So our fundamental, then 5th harmonic, 7th harmonic, 11th harmonic, and 13th harmonic. Whereas for this quasi square wave, our THD of source current is 30.4%, and it works at a lagging power factor. It takes a reactive power 3 by pi cos of alpha. Now we are require the a DC current source. AC is converted into a DC current source because we require a power to the current source inverter, and for that we are going a 3-phase current source, a PWM rectifier. So this is a particularly we are going here, that is our, we are already studied the voltage source PWM rectifier. Now we are going for a current source PWM rectifier. So what is our intention here? What we expect from this? What type of current we'll expect from the current source? So here this is our supply. This is the current source rectifier, and this is our load. Load will be here our CSI, current source inverter. I have not shown it here. We'll show it afterwards. So this is our current source inverter we are having here. The load itself is our current source inverter. So this, now our interest is we should have a DC current source. So here this current flowing will be a ID, that will be a DC current, and it is a DC current source. How is the characteristics? With respect to voltage, our ID current will remain constant, and as per the requirement, our voltage will change. As per the requirement, voltage will change. So this is our ID current and the voltage. So current should remain constant, that is ID. And load, it whatever we have shown it here is nothing but a current source inverter. And now here we are having a duality principle. Okay, duality principle between the current source PWM rectifier and voltage source PWM rectifier. Here at the output side of voltage source rectifier, we have seen that we require a capacitor. But here at output side, we require the inductor. That is a duality. In case of output side of a voltage source PWM rectifier 3-phase, we require a capacitor. We require the capacitor, but here we require a inductor at the output side. In case of voltage source PWM rectifier at input side, we require inductor, but here at input side, we require the capacitor. So that is a duality is present between this. What is our expectation from this 3-phase current source PWM rectifier? What should be the nature of current? It should take from supply. What is our expectations from this current source PWM rectifier? What type of current it will take from supply, and what power factor it will operate? What should be the nature of current it will take from supply? Anybody? What is expected current from the source this PWM rectifier, current source rectifier will take?
Sinusoidal.
So our intention is a sinusoidal current, because thyristorize we have shown that gives the Cauchy square wave, and also our PF should be power factor
1
1.
unity.
So that is the intention for which we are going for this 3-phase current source PWM rectifier. So our current, source current here, whatever here source current, whatever a source current, it should be a sinusoidal, power factor should be unity. Here we require a DC current source, and this DC current source, where it can be used, one of the application is the current source inverter or current source inverter fed induction motor, or that may be the application. We have seen the duality. Duality is present between the voltage source PWM rectifier and current source PWM rectifier. Similarity is both will take a sinusoidal current with unity power factor from the supply. Okay, that is there. And here our voltage source PWM rectifier is working in boost mode, whereas this particular it will work in the buck mode. So output voltage is less than the input voltage in this particular case. Current source PWM rectifier, the output voltage will be less than the input voltage, so it will work in the buck mode. So we can say that it will work in buck mode. Output voltage is less than input voltage. That is one peculiarity. A duality, you can solve it, you can say it. Here we require a filter, there we require capacitor. At the input side, here we require a capacitor, there we require the inductor. So these are the similarities and dualities we have studied. Now again it will be required to be a closed loop control. We are going to discuss the closed loop control in the next lecture. But what type of devices we can use it here? What is the symbol? Can you identify name of the device used here?
GTO.
Here it is a GTO. The symbol is a thyristor symbol with just get crossed. Okay, this is symbol of thyristor with get crossed. It means that it will be a symbol of GTO. The device used is the GTO. High power applications we can use. And now here we have seen that here. This is again a power flow is bidirectional. Are you getting what I want to say? The power flow here in this case is also bidirectional. Means power can flow in both directions, is it right? This is a power can flow from AC side to DC side, or from DC side to AC side. Power flow is in both directions. But what will happen to the IDC value? Is the direction of DC current changes? Is the direction of DC current will change for change of power flow?
No.
No, because devices are indirectional. So power flow will be changed. Suppose for this AC side to DC side, this will be a voltage polarity appearing across the rectifier. If power flow is reversed, our polarity has to reverse. This is our polarity, we have to reverse the polarity. So power flow is reversed. So here we require device which is having both forward voltage blocking as well as reverse voltage blocking. Forward voltage blocking as well as reverse voltage blocking. IGBT, if you take the IGBT, I'll just draw the symbol here. This is our symbol of IGBT. This is symbol of IGBT. For particularly IGBT, if you say here, they will block the forward voltage, but reverse voltage blocking capability is very less. So if you want to use IGBT particularly for this, then for reverse voltage blocking, we have to use the diode in series with that. To use the diode in series, MOSFET or IGBT, both have forward voltage blocking capability. They are having very, very less reverse voltage blocking capability. So if you want to use the IGBT here, how to use it? We have to put a diode in series. What is purpose of diode? For what purpose we are using the diode?
Reverse blocking.
Reverse voltage blocking capability we can obtain with the help of. Why reverse voltage blocking is required? Because power flow is reverse. And how the power flow is reversed? Power flow is reversed by varying the polarity of DC voltage at this input side, output side, or polarity of DC voltage will reverse. And for that, these devices we should require both a forward voltage as well as reverse voltage blocking capability. And for that, if you want to use MOSFET or IGBT, we have to put the diode in series with the device for reverse voltage blocking capability. And GTO, we have seen that GTO is having both forward voltage as well as equal, like a thyristor. Thyristor is having a forward voltage blocking and reverse voltage blocking ratings are the same. Similarly, a thyristor GTO also our forward voltage blocking and reverse voltage blocking ratings are same. So IGBT, single IGBT can be used here, but if you want to use the IGBT or MOSFET, we have to put a diode in series with this. And now whatever we have to discuss about the control of this. So we'll just whatever discussed we just summarize. So here we have seen that we at input side capacitor is required and output side at inductor is required. And we have just discussed what devices we require. We require a GTO, we can use it as it is, but IGBT we have to be with a diode, series diode for reverse voltage blocking capability. And now here one important condition, here capacitors are there. Here capacitors are there. So we cannot short the input side. That is a constraint particularly. Here our input side should not be a shorted. We cannot short the input side. Means here we cannot short the input side means we cannot switch on two upper devices simultaneously. Is it right? If suppose S1 and S3 are on, what will happen? A capacitor will be shorted between these lines. Is it right? These two capacitors will be shorted. So here we cannot switch on these two. So there will be always one device from upper is on, one device from lower is on. Are you getting? There should be a one device, two devices we cannot make it on, or three devices we can't make it on. In case of this particular, in case of voltage source inverter, upper three can be made on or lower three can be made on. That is possible in case of VSI. Here in case of VSI, we cannot on two devices in the one leg simultaneously. Here the devices in one leg can be made on. So S1 and S4 can be made on at a time. Similarly, S3 and S6 can be made on. S5 and S2 will be made on simultaneously. But here S1, S3, S5 cannot make it on simultaneously because our capacitors will be shorted. Similarly, S4, S6, S2 we can't made it on simultaneously. Whereas in case of VSI, we have seen it here, we cannot switch on the devices S1 and S4. Otherwise, what will happen? DC link will short circuit. But here S1 and S4 can be made on. S3 and S6 can be made on. S5 and S2 can be made on simultaneously. Or all these six can be made on, no problem. Okay, all six can be made on, or two legs can be made on simultaneously. Okay, one leg we can made it on, not all if you made it on, definitely the capacitors will on. So one leg can be made on, no problem, but three upper cannot be switched on simultaneously, may not on. Similarly, three lowers cannot be on. So here now if you see it here, so this particular device, one device from upper and one device from lower. So if you want to be one device from on from one side, other device from on from lower, so maximum conduction period of each device, we are operating with a pulse width. But if you not use, let us assume that pulse width, then also this may be on for 120, this may be on for 120 degrees. But okay, but here our, you can see it here, it may be a, our currents taken from the supply is almost sinusoidal. So input should not be short circuited and output should not be the open circuited. And our output voltage is a DC current source. Now, why we are using the capacitors? We have seen that at input side we are using these capacitors. And why we have to use these capacitors? They will assist for commutation of the devices and filter out harmonics. They are having two purpose: commutation. They will assist the commutation. Devices are self-commutated, but we are having a assistance is also provided and filter out the harmonics. Whereas capacitor size depend. There are so many factors for capacitor size: rectifier switching frequency, required line current THD, and supply power factor. So if you want to have, we can get a unity power factor, but for that, this sizing of capacitor is very, very important. And the size of capacitor or rating of capacitor depends upon, one is switching frequency, then current THD, how much we require, and the power factor. And here we have seen that this particular we are using for very high power current source P WM rectifier, not using in few kilowatt. We are going for a megawatt range, and in that case, when we are going for megawatt range, definitely our switching frequency, particularly a switching frequency, will be few hertz, maybe 400 hertz, 800 hertz, maybe less than 1 kilohertz. That will be a switching frequency of this. So PWM techniques that we can discuss in the tomorrow's lecture. So any questions what we have discussed today? Today we discuss one application of three-phase voltage source PWM rectifier, and that application is a variable speed constant frequency wind generation. And here we have seen that current taken, here machine currents are sinusoidal, current given to the grid are also sinusoidal, no power quality issue. But this inverter which is connected to the grid will solve some of the grid problems. It will reactive power support. This particularly inverter will provide a reactive power support to the grid. Depending upon requirement, it is possible it can supply the reactive power or it can absorb the reactive power. Okay, that is additional advantage of this particular scheme. So these are two applications. So we have discussed about PWM rectifiers. One is AC drives, that drives maybe induction motor drives, synchronous motor drives, and BLDC drives, any drives. And then we have seen a variable speed constant frequency wind power generation. Here we have shown an induction generator. Here you can also use as a synchronous generator, field wound synchronous generator, or permanent magnet synchronous generator can be used, and same scheme can be implemented. And now after that, our interest is we have shown this LCI fed synchronous motor drives, load commutated inverter fed synchronous motor drives, and in that we have shown that this particular drive we are using for megawatt capacity, and a particularly here input current is the Cauchy square wave and power factor is 3 by pi cos of alpha. And our interest is we want to go for a similar scheme uh, for this particular with the help of PWM current source rectifier. And for that we are having this is circuit diagram particularly for the current source PWM rectifier. So remaining things we discuss next time. Any questions? Any doubts?
No,
Okay,
sir.
so okay, so we stop here today.